This is a problem from the Walker textbook that is called a ballistic pendulum problem, but it combines conservation of momentum and conservation of energy. And so this is actually how they used to figure out how fast the bullet was going before high-speed cameras were available. So the situation is that someone's going to shoot a bullet into a wooden block that is hanging from strings from like the ceiling. So the bullet's going to hit the block and stick into the block, and then the combination is going to swing. And by measuring how high the pendulum swings upward, you can figure out how fast the bullet was going before it hit the block. So we're splitting this problem into two parts, and I stole a diagram from another book, but it's got a nice separation of the two parts of the problem. So when we put this into pieces here, we've got part one, which is a conservation of momentum part. So that's this part here. So we know that this is a completely inelastic collision because the bullet sticks into the block. And energy is not conserved, but momentum is, because nothing's interfering in that moment before and after the collision. But then after the collision, we're going to assume that there's no air resistance, and then like the string is perpendicular to the motion of the block, so it's not doing any work on the block. So then in this part here, where the swinging action, as long as there's no air resistance, then we can say that energy is conserved for this portion of the problem. Okay, so then we actually have to solve part two before we can solve part one, because we don't even know the speed of the bullet when it hit the block. That's what we're trying to find. Okay, so, but we do know that it swung up to a certain height. So if I'm trying to label this here, I would say like from the center of mass right here to the center of mass here, this height is 6.3 centimeters or 0.063 meters. Final height above where it began. So I'm getting some potential energy there. So when I do part two, then I'm going to say all of the kinetic energy it had to begin with is going to be transferred into, gravitational potential. Let's put that in blue. And so then 1/2 the mass of the, I'm going to put little b.
Senor Hurtado, please come to the main office. Senor Hurtado, please come to the main office immediately.
Now, this is the initial velocity, but it's really, I'm talking about the velocity after the, at the beginning of the swing. And then this is going to be mass of bullet plus block times g times the final height. Okay. So this is going to let me solve for the velocity, like initial. But that's really following the collision. So here, I could plug in the masses, but they really cancel out. So I'm going to cross those off. And then I can find vi squared is equal to 2 times 9.8 times 0.063. So then I get 1.1. I'll keep an extra sig around here, meters per second. So then that was right here, okay? Right at this moment after the collision. So now I'm going to use that as my final velocity for part 1. Okay, so then I'm using conservation of momentum to solve for the velocity of the bullet at the very, very beginning of the problem. So now I do need the masses. If I've got the mass of the bullet, I'm using little b times the initial velocity of the bullet plus the mass of the big block. Now, it's got no velocity to begin with, but I'll leave it in there for now. And then the two combined times their final velocity together. Okay, then this is 9.5 grams, but let's put that into kilograms. So this 0 is it's just hanging there, and then the combined mass, if I put all that together, the block was 5.4 plus the bullet I'm just checking my math here. 5.8. And then I'm taking that velocity that I just found. Okay. And then I can solve for VIV. So when I do that, on the right-hand side, I basically get 6.00. So then when I solve for the initial velocity of the bullet, I should get a very large number. So let's go really fast. So I get 632, and then I think the book, just for sig figs wise, rounded that to 630 meters per second. Okay, so this is called a ballistic pendulum, coming from the word ballistics that has to do with bullets. But that is an example of using both conservation of energy and conservation of momentum.